What if the most confusing chemistry problems actually follow a simple, predictable pattern? A pattern that, once revealed, will make even the toughest calculations crystal clear. Today, we're not just solving problems, we're decoding the logic behind them, transforming complex equations into straightforward steps you can master. Whether you're struggling with molar mass, limiting reactants, or tricky empirical formulas, this session is your blueprint. We'll walk through challenging questions, breaking down each solution methodically. Get ready to finally understand how to ace these calculations. Question 1. The mystery gas X. Let's dive into our first challenge. Imagine you have a gas, X. You know its mass is 6.23 grams and it occupies 1.12 liters at standard temperature and pressure, or STP. Your goal: find its molar mass. Remember, molar mass is simply the mass of your substance divided by the number of moles. We've got the mass, 6.23 grams. But here's the crucial step. How do you find the number of moles from a volume at STP? It's easier than you think. At STP, 1 mole of any gas occupies 22.4 liters. So take your gas volume, 1.12 liters, and divide it by 22.4 liters per mole. That gives us exactly 0.05 moles. Now, we put it all together. Molar mass equals 6.23 grams divided by those 0.05 moles. Your answer? A precise 124.6 grams per mole. See how that pattern unfolds? Question 2. Who has the most molecules? Next up, a common trap. Which sample contains the largest number of molecules? You're given different substances with varying masses. Here's the secret. To find the largest number of molecules, you just need to find the sample with the largest number of moles. Why? Because the number of molecules is always directly proportional to the number of moles, thanks to Avogadro's number. So for each sample, we'll calculate its moles using the formula moles equals mass divided by molar mass. Let's break it down. 1 gram of hydrogen, H2. Its molar mass is 2 grams per mole, 2 times 1. So 1 gram divided by 2 gives you 0.5 moles. 2 grams of nitrogen, N2. Molar mass is 28 grams per mole, 2 times 14. That's 2 grams divided by 28, approximately 0.071 moles. 4 grams of oxygen, O2. This is simply molar mass is 32 grams per mole. That's 4 grams divided by 32 for 0.125 moles. 11 grams of carbon dioxide, CO2. Molar mass is 44 grams per mole, 12 plus 2 times 16. So, 11 grams divided by 44 gives you 0.25 moles. Comparing these values, 0.5, 0.071, 0.125, and 0.25, it's clear hydrogen has the largest number of moles at 0.5. And that means hydrogen contains the largest number of molecules. Imagine a hypothetical reaction where A plus B reacts to form products. What happens when you mix 3 moles of substance A with 2 moles of substance B? Which one runs out first? The limiting reactant is the one that's completely used up, dictating how much product can form. To find it, we calculate a mole ratio for each reactant. Take the given moles and divide by the moles shown in the balanced equation. For substance A, you have 3 moles given, and the equation uses 3 moles. So 3 divided by 3 gives a ratio of 1. For substance B, you have 2 moles given, and the equation uses 1 mole. So 2 divided by 1 gives a ratio of 2. Comparing the ratios, 1 for A is smaller than 2 for B. This immediately tells you that A is your limiting reactant. It's the one that gets completely consumed in the reaction. Question 4. Iron to iron chloride. Ready for a stoichiometry challenge? We have a reaction. Iron Fe plus 2HCl reacts to form iron 2 chloride, FeCl2, plus hydrogen gas, H2. How much iron 2 chloride is produced if you start with 28 grams of iron? First, look at the molar relationship from the equation. 1 mole of iron produces 1 mole of iron 2 chloride. Next, we convert these moles into masses using their molar masses. Iron Fe has a molar mass of 56 grams per mole. Iron 2 chloride, FeCl2, has a molar mass of 127 grams per mole, 56 for Fe, plus 2 times 35.5 for Cl. So, 56 grams of Fe will produce 127 grams of FeCl2. Now, for our 28 grams of Fe, how much FeCl2? It's a simple proportion. Multiply 28 grams of Fe by 127 grams of FeCl2. Then divide by 56 grams of Fe. You'll find you produce 63.5 grams of iron 2 chloride. Question 5. Sodium atoms to mass. What is the mass of 3.01 times 10 to the 23 atoms of sodium? This might look in. We know mass equals the number of moles multiplied by the molar mass. The molar mass of sodium, Na, is 23 grams per mole. That part is easy. The real task is finding the number of moles from those atoms. Remember Avogadro's number? It's 6.02 times 10 to the 23 atoms per mole. So, divide your given number of atoms, 3.1 times 10 to the 23, by Avogadro's number. This calculation gives you exactly 0.5 moles. Now, multiply those 0.5 moles by sodium's molar mass of 23 grams per mole. The result? 11.5 grams. See, even large numbers become manageable. Question 6. Decoding a hydrocarbon. This next problem is a true detective case. When 50 milliliters of an unknown hydrocarbon burn, they produce 200 milliliters of CO2 and 250 milliliters of water vapor at STP. Can you figure out its molecular formula? The general combustion equation for a hydrocarbon, CXHY, is CXHY plus O. The key here is that at STP, volumes are directly proportional to moles. So let's convert our volumes to moles. Remember, 1 liter equals 1,000 milliliters. Hydrocarbon, 0.050 liters divided by 22.4 liters per mole equals 0.00223 moles. CO2, 0.20 liters divided by 22.4 liters per mole equals 0.00892 moles. H2O, 0.250 liters divided by 22.4 liters per mole equals 0.0116 moles. Now, to find the simplest whole number ratio, divide all these mole values by the smallest one, 0.00223 moles for the hydrocarbon. Hydrocarbon, 0.00223 divided by 0.0223 equals 1. CO2, 0.0892 divided by 0.0223 equals 4. H2O, 0.0116 divided by 0.0223 equals 5. This means which of these gases has a mass of 7 grams for 0.25 moles? This question is essentially asking you to find a gas with a specific molar mass. To find that magic number, just divide the given mass by the given moles. 7 grams divided by 0.25 moles. That gives you 28 grams per mole. Now, let's calculate the molar mass for each option. C2H6 ethane. 2 times 12 plus 6 times 1 equals 24 plus 6 equals 30 grams mole. Not our gas. Just remember, the 2 times 12 plus 4 times 1 equals 28 grams mole. Bingo. Nitrogen gas, 2 times 14 equals 28 grams mole. Also a match. CO, carbon monoxide, 12 plus 16 equals 28 grams mole. Another match. Here's an interesting point. Depending on the options provided in a multiple choice setting, several gases can have the same molar mass. In this case, ethene, nitrogen, and carbon monoxide all fit the criteria. If it's a single choice question, typically the first matching option or a specific context would be implied. But now you know how to identify any gas with that molar mass. Question 8. Empirical formula of nitrogen oxide. Let's find the empirical formula of a nitrogen oxide. You have a 2.31 gram sample with 0.68 grams of nitrogen in it. First, let's find the mass of oxygen. Simply subtract the mass of nitrogen from the total sample mass. 2.31 grams minus 0.68 grams equals 1.63 grams of oxygen. Now for the empirical formula steps. 1. Calculate moles for each element. For nitrogen N, 0.68 grams divided by 14 grams per mole atomic mass, approximately 0.048 moles. For oxygen, 1.63 grams divided by 16 grams per mole atomic mass equals 0.102 moles. 2. Find the simplest mole ratio. Divide both mole values by the smallest one, which is 0.048 moles for nitrogen. Ratio not 1:5, which comfortably rounds to 2. So your empirical formula is NO2. You've just distilled a complex compound down to its simplest essence. If a hydrocarbon burns, forming 2.2 grams of carbon dioxide, CO2, what is the mass of carbon that was originally in that hydrocarbon? This is a classic conservation of mass problem. Every carbon atom from the hydrocarbon ends up in a CO2 molecule. So, if we know the carbon in CO2, we know the carbon in the original hydrocarbon. From the formula, 1 mole of CO2 contains 1 mole of carbon. Let's convert this to mass. Molar mass of CO2, 12 C plus 2 times 16 O equals 44 grams per mole. Molar mass of C, 12 grams per mole. So, 44 grams of CO2 contain 12 grams of carbon. Now, set up a proportion for your 2.2 grams of CO2. Multiply 2.2 grams of CO2 by 12 grams of C. Then divide by 44 grams of CO2. The mass of carbon is 0.6 grams. That's the power of stoichiometry. Question 10. Molar concentration calculation. You have 2 grams of potassium nitrate salt, KNO3, with a molar mass of 101 grams per mole. You dissolve it to make a solution with a volume of 0.5 liters. What is the molar concentration of this solution? Molar concentration, or molarity, is defined as the number of moles of solute divided by the volume of the solution in liters. First, let's find the number of moles of potassium nitrate. Take the mass, 2 grams, and divide by its molar mass, 101 grams per mole. That gives you approximately 0.0198 moles. You're given the volume directly in liters, 0.5 liters. Now, just divide the moles by the volume. 0.0198 moles divided by 0.5 liters. That's approximately 0.0396 moles per liter, which we can round to 0.04 moles per liter. Simple as that. Question 11. Antimony phosphate formula. Given the formula for antimony oxide is Sb2O3 and sodium phosphate is Na3PO4. What is the formula for antimony phosphate? This is about understanding valencies. From Sb2O3, we see that antimony, Sb, has a valency of 3, because oxygen has a valency of 2, and they swap. Sb takes 2, O takes 3, simplified to Sb2O3. Wait, this is incorrect logic. Sb2O3 means Sb is plus 3, O is minus 2. So 2 plus 3 minus 2 equals 0. Therefore, Sb's valency is 3. From Na3PO4, we see that phosphate, PO4, has a valency of 3, because sodium has a valency of 1, and they swap. Now, to make antimony phosphate. Antimony, Sb, has a valency of 3. Phosphate, PO4, has a valency of 3. When both elements or polyatomic ions have the same valency, they essentially cancel out and combine in a 1-to-1 ratio. So the formula, 10 grams of hydrogen gas, H2, react with an abundance of oxygen gas, O2, according to the equation. 2H2 plus O2 equals 2H2O. We need to calculate the volume of oxygen reacted at STP and the mass of water vapor produced. Let's tackle the oxygen volume first. From the equation, 2 moles of H2 react with 1 mole of O2. Convert 2 moles of H2 to mass. 2 moles times 2 grams per mole equals 4 grams of H2. Convert 1 mole of O2 to volume at STP. 1 mole times 22.4 liters per mole equals 22.4 liters of O2. So 4 grams of H2 reacts with 22.4 liters of O2. If you have 10 grams of H2, how much O2? Use a proportion. 10 grams H2 times 22.4 liters O2 divided by 4 grams H2 equals 56 liters of O2. Now for the mass of water vapor produced. From the equation, 2 moles of H2 produce 2 moles of H2O. Convert 2 moles of H2 to mass. 2 moles times 2 grams. If you have 10 grams of H2, how much H2O? Proportion again. 10 grams H2 times 36 grams H2O divided by 4 grams H2 equals 90 grams of H2O. You've calculated both parts, 56 liters of oxygen and 90 grams of water vapor. Question 13. Largest mass challenge. Which of the following samples has the largest mass? You're given different substances and their mole quantities. The formula for mass is simple. Moles multiplied by molar mass. Let's calculate for each. First, A, 1 mole of methane, CH4. Molar mass is 16 grams per mole. 12 plus 4 times 1. So 1 mole times 16 grams per mole equals 16 grams. B, 2 moles of nitrogen. Molar mass is 28 grams per mole. 2 times 14. So 2 moles times 28 grams per mole equals 56 grams. C, 3 moles of ammonia, NH3. Molar mass is 17 grams per mole. 14 plus 3 times 1. So 3 moles times 17 grams per mole equals 51 grams. D, 20. Comparing these masses, 16, 56, 51, and 50 grams. It's clear that 2 moles of nitrogen has the largest mass at 56 grams. Question 14. Unmasking element X. An unknown compound has the molecular formula X4O6. You know that 10 grams of this compound contains 5.72 grams of element X. Your mission: find the relative atomic mass of element X. From the formula X4O6, we know that 1 mole of the compound contains 4 moles of element X. Let's set up a relationship based on mass. The molar mass of X4O6 is 4 times atomic mass of X plus 6 times atomic mass of O, which is 16. So 4X plus 96 grams per mole. The mass of X in 1 mole of X4O6 is simply 4X grams. Now, we can form a proportion. If 4X plus 96 grams of X4O6 contains 4X grams of X, then 10 grams of X4O6 contains 5.72 grams of 12 equals 40 times X minus 22.88 times X, which means 549.12 equals 17.12 times X. Finally, solve for X. X equals 549.12 divided by 17.12. You'll find X is approximately 32.12. So, the relative atomic mass of element X is 32. What a breakthrough! Question 15. Dilution dynamics. You have a solution with an initial volume of 0.45 liters and a concentration of 7.5 molar. How much water do you need to add to dilute it so its concentration becomes 5 molar? This is a classic dilution problem, and it's easily solved using the formula M1V1 equals M2V2. M1, initial concentration, equals 7.5 m. V1, initial volume, equals 0.45 liters. M2, final concentration, equals 5 m. V2, final volume, equals unknown. plug in the numbers. 7.5 m times 0.45 liters. That's the amount of water you need to add for that perfect dilution. Question 16. Avogadro's insight. Two samples of gases, oxygen, O2, and ozone, O3, have the same volume under the same conditions of pressure and temperature. In what aspect do these two samples agree? This question directly tests your knowledge of Avogadro's hypothesis. It states that equal volumes of different gases under the same conditions of pressure and temperature contain equal numbers of molecules. So if O2 and O3 have the same volume, at the same temperature and pressure, they must contain the same number of molecules. It doesn't matter that their chemical composition is different. The number of particles is the same. Powerful insight, isn't it? Question 17. Total moles after reaction. 1 mole of ethene gas, C2H4, burns according to the equation. C2H4 plus 3O2 is 2CO2 plus 2H2O. What is the total number of moles of gases and vapors present at the end of a reaction mixture consisting of 1 mole of ethene and 4 moles of oxygen? This is a two-part limiting reactant problem. First, let's find the limiting reactant. We'll use our mole ratio trick. Given moles divided by equation moles. For ethene, C2H4, 1 mole given divided by 1 mole from equation equals 1. For oxygen, O2, 4 moles given divided by 3 moles from equation equals 1.33. Ethene has the smaller ratio. 1 is less than 1.33, so it's the limiting reactant. It will be completely consumed. Second, calculate the moles of products formed. Since 1 mole of C2H4, our limiting reactant, reacts, the equation tells us it produces 2 moles of CO2 and 2 moles of H2O. That's a total of 4 moles of products. Third, calculate any remaining excess reactant. Ethene is limiting, so oxygen is in excess. Since 1 mole of C2H4 reacted, 3 moles of O2 were used. You started with 4 moles of O2, so 4 minus 3 equals 1 mole of O2 remains. Finally, the total number of moles at the end of the reaction. Sum the moles of products and any remaining excess reactant. That's 4 moles products plus 1 mole remaining O2 equals 5 moles. This meticulous breakdown gives you the full picture. Question 18. What is an empirical formula? Which of the following represents an empirical formula? This is about recognizing the simplest whole number ratio. An empirical formula is the most simplified ratio of atoms in a compound. You can't reduce it further. Let's check the options. A. N2O4 can be simplified by dividing by 2 to NO2, not empirical. B. C3H6 can be simplified by dividing by 3 to CH2, not empirical. C. NH3 cannot be simplified. This is an empirical formula. D. P4O10 can be simplified by dividing. So NH3 is our clear winner. It's the simplest expression of its components. Question 19. Lithium and lithium nitride. In the reaction, 6Li plus N2, 2-lithium nitride, what is the number of moles of lithium, Li, required to react with an abundance of nitrogen gas to produce 0.6 moles of lithium nitride, Li3N? Let's look at the stoichiometry. 6 moles of lithium produce 2 moles of lithium nitride. We need to find an unknown quantity of lithium, moles, to produce 0.6 moles of lithium nitride. Set up a proportion, moles of lithium over 6 moles equals 0.6 moles of lithium nitride over 2 moles. Now solve for moles of lithium. 0.6 times 6 over 2 equals 3.6 over 2 equals 1.8 moles. You need 1.8 moles of lithium. Another practical application of stoichiometry. Question 20. Equal volumes, equal moles. You have 3 samples of different gases at room temperature and pressure, RTP. Sample 1, 4 grams of argon gas, AR. Sample 2, 3.2 grams of oxygen. Which of the following is correct regarding the volumes of these samples? At RTP, the molar volume of any gas is 24 liters per mole. This means if gases have the same number of moles, they will have the same volume. So let's calculate the moles for each sample. 1. Sample, argon. Molar mass is 40 grams per mole. Moles equals 4 grams divided by 40 grams per mole equals 0.1 moles. Volume equals 0.1 moles times 24 liters per mole equals 2.4 liters. Sample 2. Oxygen O2. Molar mass is 32 grams per mole, 2 times 16. Moles equal 3.2 grams divided by 32 grams per mole equals 0.1 moles. Volume equals 0.1 moles times 24 liters per mole equals 2.4 liters. Sample 3. Carbon dioxide, CO2. Molar mass is 44 grams per mole, 12 plus 2 times 16. Moles equal 4.4 grams divided by 44 grams per mole equals. Calculate the mass of ammonia gas, NH3, that has the same volume as 8 grams of oxygen, O2, at room temperature and pressure, RTP. We know mass of ammonia equals its moles multiplied by its molar mass. Ammonia, NH3, has a molar mass of 17 grams per mole, 14 plus 3 times 1. The crucial insight here is that if ammonia and oxygen have the same volume under the same conditions, Avogadro's hypothesis tells us they must have the same number of moles. So, let's find the moles of oxygen. Molar mass of O2 is 32 grams per mole, 2 times 16. Moles of O2 is 8 grams divided by 32 grams per mole equals 0.25 moles. Since they have the same number of moles, ammonia also has 0.25 moles. Finally, mass of ammonia equals 0.25 moles times 17 grams per mole equals 4.25 grams. Piece of cake. Question 22. Copper oxide to ammonia volume. From the reaction, 3CuO plus 2NH3. Calculate the volume of ammonia gas, NH3, that reacts completely with 6 grams of copper oxide, CuO, at standard temperature and pressure, STP. Let's link the 2 compounds from the equation. 3 moles of CuO react with 2 moles of NH3. Now convert these moles to the units we need. Molar mass of CuO, 63.5 Cu plus 16 O equals 79.5 grams per mole. Molar volume of NH3 at STP equals 22.4 liters per mole. So, 3 moles of CuO is 3 times 79.5 equals 238.5 grams of CuO. And 2 moles of NH3 is 2 times 22.4 equals 44.8 liters of NH3. Therefore, 238.5 grams of CuO react with 44.8 liters of NH3. If you have 6 grams of CuO, how much NH3? First, find the percentage of chlorine. It's 100% minus 24.2% C plus 4% H equals 100% minus 28.2% equals 71.8% Cl. Second, let's determine the empirical formula assuming a 100-gram sample, so percentages become masses. 1. Calculate moles for each element. 1 for carbon C, 24.2 grams divided by 12 grams per mole equates 2.017 moles. For hydrogen, divided by 1 gram per mole equals 4 moles. 35.5 grams per mole equals 2.022 moles. 2. Find the simplest mole ratio. Divide by the smallest mole value, which is 2.017 for carbon. Ratio for C, 2.017 divided by 2.017 equals 1. Ratio for H, 4 over 2.017 is equal to 1.98, which rounds to 2. Ratio for Cl, 2.022 divided by 2.017 equals 1. So the empirical formula is CH2Cl. Third, calculate the molecular formula. 1. Molar mass of the empirical formula, CH2N, equals molar mass of compound over molar mass of empirical formula. N equals 148.5 grams per mole over 49.5 grams per mole equals 3. Multiply the empirical formula by N, CH2Cl3. And there you have it, the complete molecular formula. You've just witnessed how breaking down complex chemistry problems into these fundamental steps reveals a clear, actionable path to the solution. Mastering these patterns isn't just about getting the right answer. It's about building an intuitive understanding that will serve you in any scientific challenge. Keep practicing, and you'll find these calculations become second nature.